welcome to what should be the 16th lecture in the Jabrah reinforcement learning. And today we're going to start looking at temporal difference learning for the control problem. So in the last lecture, we had started looking at this new reinforcement learning algorithm called temporal difference learning, and we were doing it for the prediction problem. And we saw that this algorithm was somewhat an extension of the incremental Monte Carlo that we had looked at before, where our target now was no longer the return at the very end of the episode, but rather our estimated value for a particular state up to a certain time point. So if this doesn't make any sense to you right now, just please refresh your memory by looking at the previous lecture because we're just continuing from there. So having said that, so we are looking at control problems using temporal difference learning, and they are a bunch of algorithms that actually fit into the space that we're going to look at. One of them is quite a popular algorithm that you probably would recognize from the title, I'm guessing. So just like Monte Carlo methods, we're going to be looking at on-policy and off-policy approaches to actually achieving TD control. So, to get things started, we're going to start with our first TD control algorithm that is known as SARSA. So, let me denote it here. So, this is the first algorithm we're going to look at. It's called SARSA, and this algorithm is actually an on-policy TD control. Right. So if you don't remember from the previous lectures, we had made a distinction between on-policy and off-policy algorithms, where in the latter case we had a separate target and behavior policy. Once again, if these terms are new to you, just look at the previous lectures when we introduced this. I believe this was introduced when we started looking into Monte Carlo, so one of those lectures should be going through that. So having said that, let's actually get started with SARSA, right? So SARSA is an on-policy TD control algorithm. So the first thing we need to note, we are just going to be extending what we looked at in the last lecture, except that when we're looking at the prediction problem, we were estimating like the value of a given state, but now we are trying to estimate action values because this is usually what we do when we're dealing with the control problems. When I'm talking about action values, of course, I'm referring to state action value pairs and so on. So the first step, so our focus here would be on action values, right? This is where our focus is gonna be, and that means what we're trying to estimate, if you remember again, would be q pi s comma a, right? These are the action values that we're trying to get the value for. So before we look into the transition from state to state, but now we're looking into transition from state action to state action. So let's actually start with the update rule for this SARSA algorithm. So one thing you'll notice is that these algorithms are going to start looking very similar. They're just going to be slight modifications here and there. But these modifications, of course, have a huge impact in the learning process. So let's actually look at the update rule. So this SARSA update rule. And we notice that we actually denote it as follows. So we say q, right, of st, comma, at, right? So we want to find the value of the q value of the state action pair. How do we actually find this value? Well, we'll look at the old value q st comma at, right? And we add alpha. If you remember, alpha is just our learning rate in this case. If you remember also from constant alpha Monte Carlo, that's when we initiated it based on the weights. So we got alpha RT plus 1, right, plus gamma, which is our discount term, Q of ST plus 1, comma, AT plus 1, right, minus Q of ST, comma, AT. So if you looked into the previous lecture, you'll see that this looks very similar to the update rule that we had for the prediction problem, except that instead of QST, AT, we just had VST. We were estimating the value functions for the states, but now we're just extending it to the state action pairs. So you realize that this is pretty much the same thing we're doing, and all of the assumptions we had made before still apply here. So one thing to notice already is that the reason why this algorithm is called SARSA to begin with is that it actually uses all the quintuples here in its update rule, which is like the state, action, reward, next state, and next action, right? That's where the name comes from, right? Like, so when you look at this tuple s comma a comma the reward you get, then you end up in a new state s prime, and you take a new action a prime. And this is the sequence of events you actually follow when you're making your updates, as it will actually become apparent in a moment when we start looking into the pseudocode for this algorithm. So as in on policy methods, we continuously estimate q pi for the behavior policy pi, and at the same time we change pi towards greediness with respect to q pi. So this is actually, well, this is actually how on policy methods work, so to speak. So that's why we calling this such. And I'll make that much more clearer in a second. So let's actually look at the pseudocode for this algorithm. So as you would have already noticed, here we're just going to be looking at the different, in this lecture, I should probably mention this from the beginning, but we're just going to be looking at different algorithms that fall under this temporal difference learning for the control problem. So having said that, let me actually start with this. So we're looking at our SARSA algorithm, right? So we're looking at the pseudocode for this. So how do we actually start this? So first thing first, we need to set up some parameters, right? So we need to do some initial setup. So we set up alpha to, well, it should be between 0 and 1, as all learning rates should be. And we set up a small epsilon that should be greater than 0. So this epsilon is if you're implementing like an epsilon greedy policy, for example, and so on. So you should know what this is by now. So we're going to initialize q s comma a, right, for all for all states that are an element of s plus, and for all actions that are an element of whatever state we're in, and we're going to initialize this arbitrarily, right? That's kind of how we do that. So, and we're going to initialize q for the terminal state, right? We're going to initialize this to 0. So this just means like q terminal for any action, because once you're in a terminal state anyway, you can't take any action. That's why this is like that. So we're gonna loop for each episode. So the first thing we're going to do here is we're going to initialize S, which is our state, right? This is how we begin this. And then we're going to choose A, our action, from S using the policy derived from Q. Right. For example, this can be an epsilon greedy policy. So basically, we're in the initial state, and we choose A according to some initialized policy, because we initialize all these Q values, but we have an initial arbitrary policy that we start with anyway. So we're using that policy to determine what our action is. So again, this should be pretty straightforward. So we're going to loop for each state of the episode. So we're going to loop for each state of the episode. So what are we going to do? First, we're going to take action A, right? We're going to take action A, and we're going to observe our reward R and S prime. So again, this is all standard procedure. We take action, we observe our reward, and we observe what our next state S prime is going to be. And then this is the part we should be paying attention to. We choose A prime from S prime using the policy derived from Q. So when we now choose our A prime, the action we're going to take here, like we are choosing this using the same policy that we had here. So the same policy that we initialized before is the same policy that we're using to choose our new action. So this is why like this is an on policy algorithm, because our target and our behavior policies are pretty much the same, and the policy we're using to generate behavior is going to be the same policy that we use to update our Q function. And this we do in the next step, which is just saying QS comma A, right? This is updated to become QS comma A plus alpha times, so this is the same equation we had before, the reward we get plus gamma Q S prime comma A prime minus Q S comma A, right? And then we update S to be equal to S prime, and we make A equal to A prime. And we're going to continue this until we reach a terminal state. So this is the basic approach we use for this algorithm. So this is the SARSA algorithm. It's pretty simple. The only thing to note here is this section over here, like how we actually are updating our Q value. We are choosing A prime, right? The action, the next action, like by using our policy derived from Q. So because we're using the same policy, the same policy for behavior and as our target, this is why we are calling this an on-policy algorithm. So the parts here that are underlined in red are the very reason why this is like on policy, right? So it's a simple algorithm. It has its problems, as you can see, that it's actually depending. Like when we choose a prime here, this is actually going to depend on our our initialization for pi, our policy, because that's the policy we're using to choose our action to update here. So the variance for this is probably going to be pretty high for this algorithm. But of course, there are other algorithms that improve on this approach, and we're gonna start looking into those. So, with that said, let's actually move to our next algorithm here, and is the popular QLearning algorithm. Right, gonna start looking at QLearning, which essentially is off policy TD control. So Salsa was on policy TD control. QLearning is off policy TD control, which already, if you remember from our previous lecture, you should get that intuition that, well, it's not really intuition, but the fact that the target and the behavior policies are actually going to be different in this case. So this algorithm was one of the early breakthroughs, and it's actually used quite a bit in practice because it's very successful. And first thing first, to actually talk about this, we need to extend again from where we came from when we're talking about SARSA. So the first thing we note is the update rule. So let's start with the update rule for this algorithm. So what's the update rule for QLearning? So we notice that we've got Q, ST, comma AT, right, is updated as Q, ST, comma AT plus our learning rate alpha times RT plus 1 plus gamma, the maximum over all actions, right, of Q ST plus 1, comma A minus Q ST, comma AT. So this is how the QLearning algorithm works. So if you look at this algorithm and compare it to the one we saw before, so in terms of the update rule for SARSA, all we had to do was just look at the next action based on our existing policy. But here we are taking a maximum over all actions, like in the current policy, and this is actually the reason why this is an off policy algorithm, because we're no longer following well the behavior policy that we're using to generate and the policy that we're using to update our actual Q values. They're different because the target now is taking a maximum over all actions and so on. So already you can see why this is an off policy algorithm. So having said that, I'm actually going to start going through the pseudocode for this. So we're just going to be keeping it standard as usual. So first of all, so wait, this is QLearning, the code for that, right? And we're going to initialize the standard things, alpha to be 0, 1. So again, this is the same standard things that we do. So we initialize, I'm not gonna write everything here, but you get it. We initialize QSA, and we initialize Q terminal, So basically the same thing that we did with SARSA. You can just check that, and it's the same initialization process, yeah. And just like SARSA, again we loop for each episode. I'm gonna try to write this fast. We're going to initialize S first, our initial state, and then we will loop for each state of the episode. So for this, we're going to choose A from S. So choose A from S using policy derived from Q, right? So this is our behavior policy that we're using to choose action A. Then we're going to take action A, and we're going to observe R and S prime. So following this, the next thing we need to do is update our Q function. Now, if this is the distinction you need to take note of when we're dealing with SARSA versus QLearning. So here we're choosing A prime from S prime using the policy derived from Q. So again, our target and behavior policies here were the same. So we were using the same policy to choose A prime, which is what we're using to update here. But in terms of QLearning, we no longer choose A prime using the same policy, because QLearning is an off-policy algorithm. Instead, to update our target, we take the maximum over all actions of this. So this is essentially the update rule that we denote here. So that means Q S comma A is updated as Q S comma A plus alpha, the reward we get, plus gamma, the maximum over all actions of Q S prime comma A minus Q S comma A. So this is essentially the update rule here, and we update S, right, to become S prime, and then we will loop until S is terminal. So this is the entire QLearning algorithm in a nutshell. So again, it's not a difficult algorithm, especially if you've been following everything that has been happening before. So with that, we have covered SARSA, we have covered QLearning. Mind you, this is just an initial introduction to these algorithms. We're going to actually go deeper and deeper. But first, of course, we just need to introduce what they are and how they work. So this is just a simple introduction to what they are. So having said that, let's actually move to our next algorithm, which is expected SARSA. Now, already based on what it's called, maybe you can already try to guess what the update rule for this algorithm is going to look like. By calling it expected SARSA, you can already assume there is an expectation involved here. And this algorithm itself, it can be made on policy, it can be made off policy, depending on how you actually approach it. But I'm just going to show you how it works. I mean, what we should do here first is to consider an algorithm that is just like QLearning, right? Except that instead of taking the maximum over all actions like we're doing before, we compute the expected value, right? Taking into account how likely each action is under the given policy. That's essentially what expected SARSA is doing. So what this means is to the update rule for this. The update rule would be as follows. So you have Q st comma at being equal to Q st comma at plus our alpha, you got rt plus 1 plus gamma expectation under pi of Q st plus 1 comma at plus 1 given you're in st plus 1 minus Q st comma at. So this is essentially how it looks, but to simplify it even further for you to just better understand what's happening here, we can write this as Q st comma at plus alpha times rt plus 1 plus, so what we're doing here is we're looking at this, since we're taking an expectation, the summation over all possible future actions, but each and every one of those actions has a probability associated with them, right? So what is the probability of me taking action A given that I'm in this state st plus 1, right? Whatever that probability is multiplied by the corresponding Q value for the state action pair here, st plus 1 comma A, right, minus again Q st comma at. So again, the only difference the difference here between this and QLearning is instead of taking what do you call this, the maximum of all Q values, you might have probabilities associated with each and every action, and then you compute the expected Q value here. This is the expectation operation that's happening here. So as to what actually performs better, it depends on case to case, of course, and there are cases where expected also outperforms QLearning, and vice versa. So it actually depends on the problem that you're looking at. So having said that, we can actually look at this a bit further. So if we compute, if we have, say, let's look at the backup diagrams. So we have an action here, and in terms of QLearning, the backup diagram looks like this. So this is for QLearning, and then for expected SARSA, the backup diagram is just, well, I'm guessing you're already familiar with this, right? Because each and every one of those has a probability associated with them. So as you can see that in terms of QLearning, there is a maximum operator here. There's an operator here taking the maximum value, but in terms of expected SARSA, we're just taking the expectation. So this is the differences in how the backup diagrams for these two algorithms look like. So having said that, actually we have well, first of all, I should mention this. When we look at SARSA and we compare it to expected SARSA, we already identified that one problem that we might have with this algorithm is that it has with Salsa is that there's a lot of variance due to the randomness in how we select our actions. But by taking the expectation, we effectively reduce this variance due to the random selection of the AT plus one. So that's why in certain cases we can see why, or in most cases I guess, why expected Salsa might perform better. So having said that, I'm actually done with this particular lecture. So in the very next lecture, or which is coming soon, we're going to be looking into maximization bias and double Q learning, and we'll do a little bit of coding to see like how to solve problems, certain problems that are caused by those algorithms to begin with. So, like I already mentioned before, this was just an introduction to those to those three algorithms, and we're gonna start building on top of this, like we have done with all these other algorithms we've looked at, from the dynamic programming methods to Monte Carlo. But we'll be spending a lot of time here, so just prepare for that. So thank you for your time, and that's it from me.